According to the European Union, aviation accounts for about 12% of the total emissions of CO2 associated to transportation systems. Among the actions that are proposed to address this issue, there are the increasing efficiency of the transport system by making use of digital technologies, smart pricing, and encouraging the shift to lower emissions transport modes. The second possible action is the development of low-emission alternative energy carriers, like advanced biofuels, electricity, hydrogen, and renewable synthetic fuels. It's also important to remove obstacles to the electrification of transport, so to move towards zero-emissions vehicles. In this framework, a mid-term solution is the adoption of hybridization. Let's start with the definition. A hybrid electric power system is a system where two or more energy carriers are used to provide propulsion power, either together or independently. The energy carriers used in the aerospace application include fossil fuel, battery that store electricity, and hydrogen. These carriers are obtained from primary energy sources, and different production paths can be used. They have also different specifications in terms of gravimetric energy density and volumetric energy density that are both critical in the aerospace application, but also power density in the conversion process is important and must be taken into account in the analysis of this power system. It is also known that batteries, even with today lithium technology, are the most critical energy carriers in terms of energy and power density. And this limits the range and endurance that can be obtained with a full electric power system. Compared with conventional thermal powertrains, HEPS reduce carbon footprint because they have less or even no carbon-based fuel consumption. They reduce also noise at takeoff and landing because they can be performed in full electric operation. They increase safety thanks to electric backup operation, and hybridization can be also used to improve the transient behavior of the power system. The presence of a chemical energy carrier ensures longer endurance and range than battery electric vehicles and make it possible to charge the battery during the flight. However, the performance of HEPSs are affected by the technological limits of their component, and also by aging effects, particularly relevant for electrochemical devices like batteries and fuel cells that are prone to deterioration processes. Moreover, the fuel economy of HEPS depends on the hybridization degree, for example, how large is the battery, and also on the energy management strategy, which decides when to use the battery during the flight. These two aspects can be synergically addressed to obtain the best results in terms of environmental impact. But the environmental impact needs to be evaluated with the global emission index. In this presentation, I'll take into account in particular the application of HEPSs to urban air mobility, and in particular to the air taxi operation. Urban air mobility is considered a suitable way to reduce the traffic congestion and pollution, as well as increase mobility in metropolitan areas, and is expected to be introduced in our cities from 2025. UAM is an interesting application for electric and hybrid power system because of the short range requirements and limited speed and limited altitude of the typical mission. In this figure, we can see a parallel hybrid power system consisting of a turboshaft engine, mechanical connected to electric motors fed by a lithium battery. This is a configuration for a coaxial rotorcraft for the urban air mobility application that was developed in collaboration with Avio within the research projects of the technical district of Apulia. However, this is not the only power system considered here. In fact, the goal of this investigation was to design different solutions for urban air mobility and to evaluate their environmental impact with an appropriate global emission index. The proposed power system includes a thermal powertrain with a turboshaft connected to the rotors, a full electric system fed by a lithium battery, the parallel hybrid electric scheme shown before, and a series hybrid electric power system where the current of the battery is summed to the current generated by a PEM fuel cell system fed by a pressurized hydrogen storage system. Two different scenarios were considered in the development of the proposed power system. In the first case, we used the technology, and in the second case, we used data about expected improvements in 2035. This table shows in particular the power-to-weight ratio of the converters used in the power system, namely the turboshaft engine, the electric machine, and the fuel cell. For a battery, ranges of power density and energy density are reported because for lithium battery, it's possible to design the battery block in order to optimize power density or energy density. The hydrogen storage system is characterized in terms of storage efficiency, where an efficiency of 5% means that a tank of 100 kg is needed to carry 5 kg of pressurized hydrogen. Of course, this limits the actual energy density of hydrogen. These values of power and energy density were used to size the powered systems in order to meet the requirement of a typical mission for air taxi operation. It includes hovering takeoff, transition and climb, acceleration and climb, cruise, descent and landing. The table shows the speed and the altitude in each phase of the flight. Note that for a choice that was made in this investigation was to use the battery as only energy source in the first step of the flight, in particular in the takeoff and also in landing, in order to reduce the environmental impact when the vehicle is on the ground. The proposed power system were modeled with the approach shown in this scheme. Starting from the mission discretized with a time step of 1 second, the flight power request is calculated. This depends on the air taxi configuration and its takeoff mass, which in turn depends on the weight of the components of the power system. A static optimization can be performed at this stage to minimize the power and energy request on the mission. The second step is the application of the detailed model of the power system to calculate the fuel and hydrogen consumption and the depletion of the battery according to a specific energy management strategy. It is important to consider sufficiently detailed models because one of the advantages of the hybridization is the possibility to make the converter, namely the engine or the fuel cell, working at the best fuel economy operation point. And this is achieved by the energy management strategy. The energy management strategy can be optimized also separately or in synergy with the sizing optimization. The consumption of the fossil or hydrogen energy source and the depletion of the electricity storage system is used to calculate the global index. Before explaining how this global index is calculated, let's spend some words on the importance of the energy management strategy. Generally speaking, the goal of the energy management strategy is to minimize the fuel consumption by optimal usage of the two energy sources during the mission. Of course, in aerospace application, the problem can be also stated as an increasing of endurance or payload. In this investigation, we choose to use the battery in a limited way, so to allow electric backup. This was performed by avoiding the state of charge of the battery to fall below a specific threshold. Also, this threshold was changed according to the age of the battery, so to attain Earth-conscious energy management strategies that take into account the already mentioned aging and deterioration processes in the batteries. In the previous work, 4 different energy management strategies were adopted, including a deterministic rule-based control strategy, a fuzzy logic, a global optimization, and an instantaneous optimization energy management. In particular, the equivalent consumption minimization strategies was adopted. In this plot, we can see the results of the application of the method to 4 different missions, named A, B, C, and D. In black, we have the results of the dynamic program. The results shows how the fuel saving is strongly affected by the specification of the mission. The saving with respect to a thermal powertrain ranges between 12 for mission A and C to 24 for mission D. The other energy management strategies cannot reach the same results of dynamic programming. This comes as a little surprise because the global optimization, as the name suggests, allows us to find the best possible solution in terms of energy management strategies, but it's also a strategy that is very time consuming and also impossible to implement in reality because it requires a full knowledge of the flight conditions during the whole mission. And this must be known a priori in order to perform the optimization before the flight. The other strategies, in particular the energy consumption minimization strategies, do not require the full knowledge of the mission, and in this case similar results to the dynamic programming method can be obtained. The worst results are obtained with deterministic rule-based, while for mission C and D we have almost the same fuel consumption of a thermal power system, thus making useless the adoption of hybridization. In this last table, we can see the effect of battery aging on the fuel saving. In particular, we can see that the electric consumption, depletion of the battery, increases by 12% when the battery is at the end of its life compared with a newly installed battery. To evaluate the emission of a vehicle for urban air mobility, we consider as thermal reference some road vehicles, including a hybrid electric vehicle, a full electric hybrid vehicle. However, it is necessary to take into account that the distance from a starting point P to destination Q depends on the road network in the case of road vehicles, while a Euclidean distance can be assumed for the aerial vehicles. The ratio of the network to Euclidean distance is known in literature as security factor. Therefore, we developed a global emission index that takes into account the security factor, and we consider different values of the security factor to have sensitivity on how these parameters affect the environmental impact of a road vehicle. This slide explains how the global emission index was obtained. The tank-to-wing emissions associated to the consumption of fossil fuel are calculated with this formula, where 2.55 is the kilogram of CO2 produced per liter of kerosene, while CF is the security factor explained before. This emission factor is increased by 15% to take into account the indirect emissions caused by the production and the transportation of kerosene. In this way, we obtain a well-to-wing impact. For the electric consumption, we need to calculate only the indirect impact, and in this case, we consider the EEI, which is the electricity emission intensity of the electricity production system. The electric consumption of the vehicles expressed in kilowatt-hour per kilometer of Euclidean distance, DOD, the depth of discharge of the battery, how much the battery is discharged in the mission, and the last terms is an efficiency that takes into account the losses in the electric grid and also during the charging process. Similarly, for hydrogen-based power systems that do not produce CO2 during the flight, we have to consider indirect impact because, as for electricity, hydrogen can be produced and transported in different ways. Today's and projected values of the electricity emission intensity for Europe are shown in these plots. In particular, we can notice that today the emission intensity of European Union is 275 grams of CO2 per kilowatt of electricity produced. However, this value can range between 8 and 900 according to the different plants used for the production of electricity. It is also important to take into account that the emission intensity of the European is expected to strongly be decreased in the next decades. So we will use this prediction for the 2035 scenario. About hydrogen, it is well known that hydrogen is classified as black hydrogen, gray, blue, or green hydrogen according to the production path. The emission intensity is strongly dependent on the production path. In the case of black hydrogen produced using electricity generated by coal, we have a very high emission intensity of 20 kg of CO2 per kilogram of hydrogen. This value is very low in the case of blue hydrogen obtained from natural gas with carbon capture, utilization, and storage. Of course, the hydrogen emission index is equal to 0 in case of hydrogen produced from renewable electricity. Let's see the results of the comparison. This plot refers to today's technology and represents on the x-axis the electricity emission intensity, while the proposed global index is reported on the y-axis. The road vehicle used for the comparison is a hybrid electric vehicle, specifically the Toyota Prius. The declared fuel consumption of this road vehicle is of only 3 liters per 100 km. However, a study of the literature revealed that under realistic driving conditions, and in particular in the worst condition of traffic jams, this fuel consumption can reach very high values, about 15 liters per 100 km. So we decided to plot in this case, two lines. The dotted line corresponds to the worst case in terms of fuel consumption, but also in terms of security factor corresponding to 2.1. The continuous black line represents the best condition corresponding to the best case of fuel consumption and security factor. We can notice that despite all these effects, the road vehicle, even in the worst case, is cleaner than an aerial vehicle with either thermal or hybrid electric power system. The comparison with the full electric air taxi, represented by the green line, is not straightforward because it depends on traffic conditions and on electricity emission intensity. With 2035 technologies, we have for all powertrains lower values of the emission emission of CO2, of course. But in this case, we consider as reference car the Nissan Leaf, which is a full electric vehicle. Also, in this case, there is a certain variability of electricity consumption according to the driving condition, in particular on usage of the electric auxiliaries like the air conditioning system. And also, in this case, we have to consider the same security factor considered above. We can notice that in this case, the road vehicle is better than any other solution, and in particular is better than an electric vehicle, aerial vehicle, performing the same mission. To explain this result, let's consider the cruise power required to move an air or a road vehicle with the same mass moving at a particular travel speed. We can notice that at the same speed, we need much more power for the aerial vehicle. Moreover, an aerial vehicle moves faster than a road vehicle. In fact, one of the advantages of the urban air mobility is the reduced travel time. So, the power request of an aerial vehicle can be higher than twice the power request of a road vehicle in a realistic driving condition. So we can conclude from these results that it is meaningless to use air taxi for intercity travel, while it can, of course, if we consider only the global environmental impact as a goal, while it can be worthwhile to use this means of transportation within a congested urban area, where road vehicles are strongly penalized as shown before. Hydrogen-powered aerial vehicles were not considered in the previous analysis, and they are reported here. We can see here the global index as a function of the hydrogen production system, with very high values of emissions associated to the usage of coal. The full electric air taxi and the Toyota Prius in the best conditions are used for the comparison. Note that in this case, the best results are obtained with the hybrid electric power system powered by blue hydrogen, except for the case of very low of electricity emission intensity, where electric car is the best solution. To conclude, the optimal sizing of different propulsion systems for urban air mobility was carried out in this investigation. And among the power systems considered, we have also analyzed a hydrogen-powered system. The different configurations were analyzed and compared in terms of global environmental impact with two different scenarios. For the comparison, a new coefficient, grams of CO2 per kilometer of Euclidean distance, was introduced. Note that the emissions associated with the production and the disposal of the powertrain were not taken into account because a life assessment analysis was behind the goal of this investigation. However, this kind of analysis could change the results of the comparison. The results of the comparison between the road and air taxi showed that urban air mobility will never be more fuel efficient than a road vehicle in the case of intercity travel due to the very high power request, while blue hydrogen power solutions were found to be suitable, especially for countries where high emission intensity are associated with electricity production, to reduce the emissions of CO2 and also to reduce the traffic congestion in the urban areas. Further developments of this investigation will deal with the design and implementation of more advanced energy management strategies for the hydrogen-powered system. In particular, this strategy will be able to use the battery according to the actual status of the aerial vehicle and its interaction with the ground. Thus, we will need to develop a digital twin of a hydrogen-powered air taxi. Thank you very much for your attention. Please feel free to contact me if you have any question or for collaboration proposal. Using the QR codes, you will be able to access my papers and presentation about this topic.